Hi, Lori.
Hi,
Hey, how are you?
I'm good. I'm just charging my headphones, so
Oh, for sure.
just in case. Um,
Yeah, no, I can hear you fine, so that's great.
okay, good.
Yeah, and you're a co-host too, so you'll have the ability to share your screen.
Okay, super. Awesome. Okay. How's it going?
Oh, good. Can't complain.
That's good.
Yeah, so if you want to, you don't have to now, but like before there, if you want to have like your presentation slides on the
Yeah.
screen, that's more than okay. Yeah, and then I'll do the greeting, the intro there to you, and
Okay.
just a housewarming or a housekeeping item and pass it
Perfect.
right over.
I'm gonna do the
Do, 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 do.
review. Are you seeing it?
I am not. No.
Oh, wonder what I did. Okay. Where did Zoom go? Uh,
Oh,
got it now?
yeah, yeah, I can see your screen now.
Okay, so now I'll just go presenter view.
And then I can see I see your presenter view here, not the.
Oh, okay. That is good thing we're practicing. That's so strange. Okay. So stop sharing.
There you go.
Okay. Not sure what that was. Must have hit the wrong thing. All right.
Yeah, that's perfect.
Yay. All right. Great. Now I have to confess that I didn't practice the time. So there may be a part in the middle where I speed up a little.
Ah, that's fine.
Anyway, it's so hard. I'm
So
like,
much to cover.
well, there is a lot to cover. Like I was saying to my drafter this morning, like it could easily be an all day thing. Anyway, not that I would be prepared for that, but
Well, we'll just if you go longer, we'll just cut the Q&A out. Sometimes there's no questions at the end. Sometimes there is. It's
yeah, I know it's always it's
hit or
really hard to
miss.
prep for that.
Excuse
Bless
me.
you.
So I guess we'll just sit tight there till
Yeah,
about
no
two
worries.
o'clock, and we'll get things rolling.
Oh, I should run and grab some water. That would be smart.
We'll just give it a couple more minutes there, let people join. Okay. Good afternoon, everyone. Welcome to the Atlantic Woodworks webinar on passive house and non-residential wood buildings. To start the webinar, I'd like to introduce our speaker, Lorrie Rand. Lorrie Rand is the co-founder of Habit Studio, the leading authority on sustainable home renovations in Nova Scotia, and co-director of the Recover Initiative, a not-for-profit plan to implement deep energy retrofits at scale across Nova Scotia and Canada. Lorrie is committed to promoting high-performance buildings to clients and colleagues. She serves on the board of directors for Passive Buildings Canada and hosts the Passivists, a group of designers and builders working on passive house projects in Nova Scotia. Lorrie has nearly 20 years experience leading outstanding residential design projects and consulting on larger projects. She is proud to have worked with Anne Sinclair Architects, designing the recently completed Halifax Hospice, a notable achievement as the first residential hospice built in Nova Scotia that was also designed by an all-women architectural team. Lorrie is a certified passive house designer and has a Bachelor of Environmental Design Studies from Dalhousie School of Architecture. So I guess before we get started there, if you have any questions throughout the presentation, please type it into the Q&A box on your screen there, and we'll answer any questions you may have at the end of the presentation. So with that being said, Lorrie, I'll pass it off to you and you can start.
Great. Thanks, David. I just want to double check that you can hear me because I messed with my setup while you were talking.
Yes, I can. Yeah.
Okay, super. So thank you for having me to speak today about passive house and non-residential wood buildings. And I should start by saying that the title is a little bit misleading because we will look at some multi-family residential buildings. We're just not focusing on single family homes. And that comes with a disclaimer that my experience in passive house is mostly single family work because that's what we mostly focus on at Habit Studio. And it's also because there are not very many non-residential passive house buildings yet in the Atlantic provinces. But this is starting to change. I'm consulting on 2 right now, and I'm really hoping that there's growth in this side of the passive house industry in Atlantic Canada. And that's why I'm here to share with you to hopefully encourage other building industry professionals to work on passive house. And so I'm going to start off by going over the Passive House standard in case there's anybody who's listening who's not familiar. We'll go over the background and the basic principles and a bit about how to integrate Passive House in the design process. And then we'll talk about wood construction specifically in Passive House projects, why we should use wood, what are some of the technical considerations of using wood, and then I'll give you some examples of both Passive House assemblies and Passive House non-residential R values, which seems to be a really common question with people new to Passive House. And then we will look at some examples of wood Passive House buildings at a range of scales. And I'll share my top Passive House resources, and then there'll be time for questions. So construction and building operations account for 40% of greenhouse gas emissions, and that's probably not a surprise for anyone listening. As building industry professionals, we have an opportunity to do something about that. There are a few other professions where the choices that you make in your career can have as profound an impact on the global effort to halt and reverse climate change. I think it's our responsibility to make every building that we touch for the rest of our careers as sustainable as possible. And that's where Passive House comes in, because Passive House buildings use up to 90% less energy than code compliant buildings. But while efficiency is what Passive House is predominantly known for, the Passive House standard is first and foremost a quality standard, and it promises unparalleled occupant comfort and minimal costs of building ownership over the life of the building, as well as the highest levels of energy efficiency achievable. So this is a picture of the first Passive House. Passive House started in the late 1980s when Wolfgang Feist, who's a German physicist, and Bo Adamson, a Swedish economist, set out to use building science and economics together to design the best building they could build. And this project was built in 1991, and it's been continuously monitored since then. And so a report was recently produced documenting 25 years of monitoring data, demonstrating that the house is still performing as modeled. And I called it a house, but it's actually a 4-unit townhouse in Darmstadt in Germany. And so in terms of energy use and the condition of the building components and in the indoor air quality and general quality of interior spaces, this building is still going strong with no noticeable deterioration in performance. So that can give us confidence. A lot of people in North America still haven't even heard of Passive House, but there's 25 years of proof that as an approach, it works. So the fundamental principles of Passive House, sort of the envelope, it's an envelope first strategy where we manage the sun and we keep out the elements with the most durable envelope possible. And so we do that with high performance windows and doors and precise orientation to the best of our abilities, depending on the site and shading considerations. There has to be an airtight envelope that has to be tested and confirmed with a blower door test. And we have continuous insulation with no thermal bridges. And once you have an envelope that is that tight, it requires fresh air with heat recovery through high performance ventilation, heat recovery, or energy recovery system. And so when we optimize the performance of the building envelope, it lets us minimize the mechanical systems. And Typically, the mechanical equipment is among the most expensive elements of a building. So we can offset the costs associated with increasing insulation and airtightness by installing right-sized, high-performance equipment. And this approach is beneficial because it makes it for a durable and resilient enclosure. It also provides the highest level of occupant comfort and the best quality air. So it contributes to occupant health, and it's the lowest possible energy consumption of any buildings. I always hesitate to include this slide when I'm talking about Passive House because it's a bit confusing, but it graphs the operating costs, which is the yellow line, which go up as our insulation is poorer, against the capital costs, which go up as our insulation is better. And so the balance of that performance or the costs is the red line, which represents the total life cycle costs of owning a building. And what we're trying to do with the Passive House is to hit the spot at the lowest point on the red curve where we get the optimal performance for the lowest cost. And if we stop short of that in terms of performance, because we don't want to spend quite as much money, or perhaps we've modeled it incorrectly, we kind of get the highest cost for slightly okay performance. It really helps us to aim for that. If we spend more than we need to and go beyond that, then you've kind of spent too much for your building. So that is where the economics comes in, and it's deeply linked in the energy modeling process, and it's where the targets that the Germans, when they were writing the PHPP, the energy modeling platform, that's where it came from. And so one of the top 3 goals of the Passive House strategy is affordability. And what they're talking about isn't capital cost of the building, it's long-term affordability over the life of the building, which often represents less than, the capital costs represent less than 10% of the cost of building ownership. So this is profoundly important, and is useful in explaining to clients why spending slightly more for a high performance building is well worth the money. So this is sort of like the secret 6th principle of Passive House. Heat loss is a factor of the area of the envelope relative to the volume of the air in the building. So we want to be very strategic with the shape. A simple shape with a smaller ratio of surface area to volume minimizes the heat loss, and the reverse is true. And this isn't to say that we have to build cubes and shoe boxes, but it is something that we need to be aware of, and something that's often forgotten or downplayed in importance in a project. In North America, we have 2 options for designing and building and pursuing certification on a Passive House. So initially, the Passive House Institute began in Germany, and after a bit of time, the United States formed Passive House Institute United States. And for quite some time, they actually operated following the same Passive House targets as the Passive House Institute, but they eventually split, and it's quite confusing. I've tried to simplify it here because if you are working on a Passive House project and you're choosing to pursue certification, then you need to consider which route you're going to take. So the big difference between the Passive House Institute and FIAS is that the Passive House Institute has the same standard, the same targets rather, no matter where you are in the world. And what that means is that whether your building is in Germany or Canada or Antarctica, your building needs to hit the heating and cooling demand of 15 kilowatt hours per meter square building area, and it needs to hit the primary energy target of 120 kilowatt hours per meter square. And so if you are in a much colder place, you need to work a lot harder on your envelope to meet those targets than if you're somewhere with a more moderate climate. Both targets have an air tightness target. Well, it's comparable. It works out to being very close to 0.6 air changes per hour, but the Americans have chosen to express it as a ratio of the area of envelope to the volume, and that's so that it doesn't penalize small buildings. When you are modeling for a project for the Passive House Institute, you must use their energy modeling platform, which is called the Passive House Planning Package. And if you're certifying in the United States, you need to use a program called WUFI. And the reason, the rationale, it's funny, the Passive House Institute and FIAS had kind of a nasty breakup. And with all nasty breakups, I think they're both a little bit at fault. The United States was quite justified in their concerns with hitting the targets, both from a building science perspective and an economics perspective. And so they have what's called a climate adjusted target. And what that means is that you have slightly different targets depending on where you are in the world. And they have, sort of under the understanding that in North America, it is very affordable, or it is more economical to balance your envelope performance levels with a certain level of renewable energy through photovoltaics. And so it's next to impossible at this point, in my opinion, to pursue a FIAS project unless you are intending to include passive, or rather solar panels in your project. So that might be a reason not to pursue a FIAS certification if you're thinking of it. So the targets for your heating are slightly easier to hit, but it is more challenging to hit the primary energy targets, which are go to the total energies of the building. And here's another confusing graphic, but I think it's one you've probably seen before. This is called the McLeamy curve. And it demonstrates that the more developed a project is, the harder it is to change things. And it's usually used in a conversation promoting a BIM workflow. But it's also very applicable to incorporating Passive House into your work, into your project delivery. It's super critical at the beginning of a project that the entire consultant team understand the performance targets and the design objectives, and how their particular role is impacted by those targets. It's not impossible to make a passive house if you don't begin in pre-design or schematic design, but it will cost more money if it is introduced to the scope of work later in the process. And so the other thing that happens in passive house is maybe not a firm commitment, or it's added later in the process, is that it gives the illusion of it being an extra, because there would be a significant number of changes needed in order to make it work. So for that reason, it's strongly recommended that if you are considering making a passive house, it is part of the project right from the start. So energy modeling is critical in a passive house project. Architects and engineers have a very complex job, and essentially the job is to solve problems, and the building is something that is needed to answer the problem. And there are a list of requirements and priorities that are subject to constraints, including cost and space and codes, and also the laws of physics. The energy model will give information about the performance that will inform all of these decisions, and it can be linked to, it's linked to costs and these other factors. So a lot of the time we have to defend our recommendations for a building to a client, or sometimes to a code official, a building official. And having an energy model gives clear data to support your recommendation. It can give you a lot of confidence in advising your clients on how they can expect the building to perform, and then what it will cost them to own that building. Having said that, you should never promise that the building will perform exactly as modeled, because occupant behavior has a huge role in the way that a building functions in terms of internal heat gains, and also the variations in weather patterns year to year can have a big difference. So it's based on a set of climate data for your specific location, and of course, one year may be slightly different than the next. With an energy model, it is critical that you do it from the beginning of the project. So initially, you'll use it in schematic design to test variations on the building form and the orientation, and how those impact the building performance, to establish what R values might be needed and that sort of thing. And then the model is updated iteratively as the design is developed, so that each time you are making a change or considering a change, you test it in the model and determine whether that gets you closer or farther from the performance targets. So you don't have to certify your building. And in fact, I've lost count of the passive house buildings we have done, and we've never certified a building. We're in the process of certification on our first project. And the certification process is a rigorous third-party quality assurance process that definitely adds time to the project. And so you need to budget for that time in your design fee, if that is considered in the project. The certified passive house designer works with the design team, taking direction from the architect and the engineers, but also from the client and potentially the builders, to develop and maintain the energy model, and to advise on recommended design changes that might impact performance for the better. And then their role is also to produce a set of documentation that is sent to the passive house certifier, which would include things like building details, photographs documenting construction, and also site conditions, results of the blower door test, and commissioning of the mechanical systems. Every detail, they want to know everything about the building. And the passive house certifier reviews all of this documentation and might advise you on some problem areas, and then ultimately they submit the project to either the Passive House Institute or FIAS, whichever organization you've chosen to work with. And that process it's slightly different between those two organizations, but it more or less follows that workflow. So there's extra communications and time needed for documents coordination. So in construction, the most important thing in construction is that the builder and the contractor team understands the objectives and that they have buy-in. You Your team of builders needs to be motivated to meet the targets, and they need to be educated about the sorts of things that they might do that could negatively impact the work. Execution is 50% of meeting the targets. So you can do a bang up job in design and still fail to hit the targets if the contracting team is slack. So every trade that comes on site needs to understand that only planned penetrations can be made in the envelope, and that's usually the one single most important thing on a project. As I said before, we need to do blower door tests to confirm that the air tightness targets have been met. And blower door tests on bigger buildings can be quite technically tricky, depending on the volume of the air in the building. And in some cases, the form of the building, if you have a shape that has different wings, for example. And so you might potentially need to set up multiple fan setups in multiple doors, and sometimes you may need to compartmentalize the building, sort of seal off different bits and test them independently. And the blower door test can take the better part of a day, if not longer, with a big building. And typically there would be 2 tests at a minimum in the course of the construction, one before drywall and one after drywall once all of the services and equipment are in. And this is very important to have in your construction schedule, because you can't have people coming and going during the testing. All of the doors need to be sealed, and you know, it's quite intrusive. And so it can cause delays if the contractor is not expecting it, or if it doesn't get coordinated appropriately in the schedule. And the photo on the of the man with the blower door test is I put there to remind myself to talk about this, because this is actually from the Halifax Hospice blower door testing, and they didn't listen to us, and they had a full construction crew on site on the day of blower door testing, and they also had orientations going on for volunteers. And so it was interrupted a number of times because people were standing on hoses and hallways, and you know, various chaotic things happened. It is a hassle for sure if it's not done with minimal people on site. And the other really important thing that happens at the end of the construction process is the commissioning of the ventilation system. Often when ventilation equipment is installed, it is quite unbalanced. And so with every building, but especially with a passive house building, the commissioning, which is the process where somebody balances the airflow of supply and exhaust in all of the building spaces, that has to be done. And it can be another thing that is quite time consuming. You know, what is built is rarely matches what is modeled, and the goal is to get the performance to match exactly what the model shows. Okay, so I have raced through the fundamental passive house lessons, and now it's time to talk about why wood. The passive house standard focuses on building operational energy, occupant comfort, and health, as we've covered, but it doesn't stipulate or limit what materials might be used to achieve the performance targets. And so you have infinite choices in building your passive house building, but wood is a very advantageous option. And I'm starting with biophilia because it gets often left out. Most people find wood to be very aesthetically pleasing, but that's quite subjective. And lots of people find buildings that are made of glass and steel or masonry also very beautiful, and they're not wrong. But the value of wood for buildings goes beyond surface aesthetics. Our human brains and bodies are wired for an innate affinity with nature. We spend 90% of our lives indoors as North Americans, and that has only been our pattern for a very short time in terms of evolution. So biophilic design is an approach that emphasizes the necessity of maintaining, enhancing, and restoring the beneficial experience of nature in the built environment, and includes incorporating natural materials like wood. And research shows that occupants in buildings designed following biophilic principles experience less stress and lower blood pressure and have increased levels of productivity and focus. So beyond being beautiful, using wood has social benefits to the users and even potentially an economic benefit. Despite huge progress that we have made over the last few years in energy efficiency, buildings that are being made more efficiently than ever, our energy efficiency efforts are not keeping up with the pace of rising floor area. So energy demand over the last decade has continued to rise. Getting control of our emissions, the emissions that we produce between now and 2050 will determine whether or not we prevent the worst effects from climate change. Currently, operational emissions account for nearly 75% of building sector carbon emissions, and the balance comes from embodied carbon emitted in the fabrication of building materials and the construction process. And as grids decarbonize and building efficiency continues to improve, by 2050, embodied carbon will represent half of the greenhouse gas emissions from buildings. So this means that to meet our global climate goals, we must specify products with small carbon footprints. I hesitated to include this graph because it is from FP Innovations, so it's a funded study by the wood industry. However, it was done by, or it's done with the Athena calculator, which is a good calculator. And that looks at the embodied energy of wood and steel across, not just the embodied energy, but other, the embodied energy in construction, but also water and air pollution and other factors. So it's important that we understand the impact of what it is we're building, what it is we're putting in our buildings. Chris Magwood is a natural builder in Ontario who's done some groundbreaking research on embodied carbon in buildings. And the graph above is taken from his thesis, where he compared the lifetime carbon or CO2e emissions for both code compliant and passive house buildings using 4 different construction approaches. And I'm not going to go into what the assemblies are for those 4 buildings, but basically he looked at what assembly would give us the highest embodied carbon, what is the typical scenario, what gets built. He's in Ontario, so he was using code compliant Ontario building. And then the best version of conventional construction and the best version of sinking the most carbon, the most beneficial carbon products in the building. And I could talk all day about this information, so I want to do it quickly, but still get at the essence of it. You know, the the important information for people designing passive house projects is that the best building and the worst building in his calculations are both passive houses. So a passive house that is made with materials with high embodied carbon is the worst building in the bunch. And a code compliant building made with plant-based materials is actually better for the planet by quite a bit than a passive house built with predominantly foam-based insulation and concrete. And then if we look at that, those same numbers and factor in the operational carbon, because the excuse for using high embodied carbon products is always that they are going to save more energy than the damage they're doing in emissions during construction and fabrication. And this proves that that is not the case. So nothing really changed in this graph. He's assuming that these buildings are heated with a heat pump because that is how buildings typically are now in Ontario. When I learned this, it really changed the way that I viewed the buildings, all of the buildings that we're building, but especially the passive house buildings, because you know, it's an argument for sinking as much wood and other plant-based materials in the building. And so any plant-based material is between 40 and 50% carbon. And so when we're looking at opportunities for storing carbon in buildings, we can look beyond the structure of using wood to also include plant-based insulations. And so this slide is just a number of examples of plant-based insulations that are available. Cellulose is readily available. It's the cheapest insulation going, and as sort of the #1 recommendation that I would make for making your building a carbon storage device. Other products that hopefully they're available in North America now, but they're not easy to come by, are wood fiber-based board insulations, which can serve as structural sheathing. And these two that I'm showing are Gutex and Pavitex. Gutex is brought in from Europe. Both are brought in from Europe. But Pavitex was actually just bought by Suprema in the last little while. And so I'm hoping that they are able to expand the North American availability of it. So carbon, I've talked a lot about carbon, I'll move on. But while we're talking about insulation, thermal performance in a passive house is critical. The thermal conductivity of wood is very low. It's kind of more of a poor insulator than it is a conductor. So the R value of framing lumber is about 1.1 to 1.3 per inch. So if you're using lumber in your stud assembly, your nominal value of your insulation is derated in the effective R value, but not that badly compared with steel, which when you're looking at super insulating your assemblies, it effectively diminishes the value, the R value, by 50 to 60%. And so you need to spend a lot more money on insulation if you're going to choose to use steel in an exterior wall in a passive house. So other great things about wood, structurally, it's strong, it's durable, it's resilient. That's a picture of a CLT building being tested on the world's largest shake table in Japan for seismic performance. And that particular building went through 14 tests with very little to show for it. So we often, in design school, I was taught that wood is great in compression and steel is great in tension, but wood and steel are actually both strong in compression and tension. But wood is lighter than concrete or steel, so it's easier to work with on site, and it has been shown to outperform steel seismically because it absorbs the vibrations better and can take repeated stresses without failure in a better way than steel can. And cost. So the cost of a 2x4 this week, I looked it up yesterday, is 227% more than the cost it was a year ago. And the cost of a sheet of OSB has gone up by nearly 300%. So this isn't the greatest timing for a presentation on the affordability of wood, to talk about the affordability of wood. But affordability is relative, and despite the current spike in wood, it actually, I would argue, is still an economical option. And the cost comparison of wood versus steel or masonry for a particular building is always going to vary depending on the details of the particular building. But research around the world is showing that the comparative costs of wood, and I'm talking now about large wood buildings versus steel or concrete-based buildings across a variety of building types. The costs associated with mass timber as it becomes less experimental and more accepted by building codes is anticipated to drop. And one notable cost driver right now for mass timber is the relatively small supply. And so as, you know, I just read that we have a new CLT fabrication place in Canada within the past month. You know, as this becomes more available and as we have more people experienced in designing and building these buildings, the prices will come down. And one of the reasons that the costs come down is because the costs of a project are not simply the costs of the materials. So this is a passive house in North Vancouver. It's a 3-story building that was erected in 10 days. And it was the reasons for choosing to build it as CLT or as a panelized option, it is CLT, were because of a very tightly constrained site. So, so cost was less of a factor, and the weight was less of a factor. It was the fact that they could do it in such a short time that was a really driving factor in the decision to build this building. And here's another bigger mass timber building. This one is, the previous one was a commercial building, but this is a multifamily residential building, 9 stories in less than a month with 4 guys. But this is embarrassing. I had to include that building because it was pretty, but I cheated because that one wasn't a passive house. But it is a beautiful example of mass timber. And I should say that modular and prefab passive house high rises can be done with steel and concrete. But the technical challenges, there's different technical challenges with them because thermal bridging becomes more of a factor. And as we know more and more about embodied carbon, more designers are going to choose to go in the direction of wood. And really, I should say that the embodied or the operational carbon savings for a steel or concrete tower are never going to offset the embodied carbon from the construction. So what are some things we should be aware of when we're building with wood? This isn't just applied to wood, but we all know that the one big thing, the most frequent thing that we battle in making buildings is related to moisture. Wood has the ability to absorb and release moisture, so over the life of the building, wood is actually more resilient in its response to water. But it's really critical, particularly with large buildings and buildings with deep wall cavities, that they are built as quickly as possible and that we protect them during construction to prevent water absorption. Because in buildings with a lot of wood and also with other plant-based insulation materials, they could potentially never dry before mold and rot set in. So that's a big advantage of doing a mass timber building in a modular or prefabricated approach, because the speed of execution reduces the risks associated with exposure during a longer build. Additionally, the moisture risk doesn't go away once the building is finished. We need to protect the building from weather over the life of the building, and so detailing the envelope on a larger building, passive house or not, a taller building is exposed to more wind and rain, and so more care needs to be taken with the air barrier and the WRB, the water resistant barrier, and the cladding system. Sorry, I'm realizing that's a really blurry slide now that I see it on the big screen. And I stole this slide from Graham Finch, who did a presentation a few years back for Woodworks here in Halifax about tall wood. Excuse me. Shrinkage and settlement and higher wind loads are factors to be, they're all manageable, but they need to be carefully engineered. Excuse me, just 1 minute. So, can you hear me? So, this issue is a particular concern if you're designing a building that's a hybrid building that mixes wood with concrete or steel, because they're not going to settle in the same way or at the same rate as the wood components. And so as you increase the stories of the building, this becomes amplified. This can also impact the longevity of the finishes if cracking were to happen on the inside. But in a passive house, there's a more serious problem, because settlement or shrinkage or wind loads, if they're very strong and poorly designed for, the movement is enough to could open gaps in the openings or connection point joints, and at pipe penetrations or even pipe connections. So Woodworks definitely has more resources about this, including the very detailed presentation from Graham Finch. And fire protection. So some of the slides I'm going to show you in a couple of minutes show examples of mass timber that has been left exposed in buildings. To my knowledge, this is always a negotiation with the building officials. There are things you can do. Obviously, sprinkling a tall building is essential, and there are fire retarding treatments, but there's when you're going to expose wood, the details need to be carefully worked out. So there's engineering involved. There's no cut or dry or prescriptive rules around this yet. And that is a picture from Moriyama and Tashina architects project, proposed project at George Brown College, where they're going to be building, I think it's a 12-story mass timber student residence. And I don't remember if that building has passive house targets, but it does have very high performance targets, and it's a beautiful building. And so I'm hoping they get to build it the way it looks in this rendering, but that is a conversation they're going to have. So I'm going to quickly show you some examples of assemblies that can work for passive house. And this is an example of a Larson truss, sort of Larson truss or a TJI based assembly where you use an I-joist or a homemade I-joist to contain dense packed cellulose. Is a very common passive house wall. It can be stick framed or panelized like in this picture. And this is suitable for anything up to perhaps 3 or 4 stories. Probably, if you know, the code wouldn't permit it to go beyond that. And it's really common in the northeastern parts of North America. Nova Scotia certainly has a few, and you know, through to Ontario and New England. And another really common option for similar applications would be the double stud wall with cavity insulation. And again, suitable for 3 to 4 stories max. This is a really, the double stud wall is a very flexible option because if you need higher R values, you can just make it deeper. However, it's a little bit less easy to accomplish the air sealing details at the material connections and also at things like windows and doors. So it relies on, you really need an experienced crew for this kind of wall. Those previous 2 slides were I cheated again because those were houses. Those were Habit Studio passive houses. But this one I borrowed from a friend, a colleague in Quebec. And this is actually a wedding venue. So it's a passive house wedding venue in Wakefield, Quebec, done by Homasol. And the wall assembly for this is a kind of, it's sort of a double stud wall, but really the crux of it is a wood stud plus outboard rigid insulation. And so it's a 2x8 wood stud with Roxol insulation in the cavity and Roxol insulation, about 4 inches of it outboard of the wood studs. And then there is an interior 2x6 service cavity, which is also insulated. And that is a much more robust wall than you'll typically see in the Maritimes. You know, Quebec is a fair bit colder. And again, this is a 3 to 4 story wood solution. And incidentally, this building was built in a panelized way, although the architects say that they would do it differently another time. The 2x8 and 2x6 walls were actually prefabricated and shipped to site as panels. And then this is sort of an example of a hybrid prefabricated and site build approach. So the wall panels were made, but they weren't insulated. And so if they were to do it again, they would probably panelize the whole thing and save a lot more time. And finally, mass timber. So mass timber can obviously be higher than 4 stories. And if you're located in Central Europe, you can get the R value needed for a passive house with a solid CLT wall and nothing more. In Halifax, our CLT wall would need to be about 3 feet thick. So it's not a viable option, but you could make a code minimum building with solid CLT in Nova Scotia. So mass timber, in theory, lets us do solid wood assemblies, but in reality, in the Maritimes, we would need to include a service or an additional section of wall. So our values, I'm realizing I have many more slides and lots more to say. So I'll try to be quick. Everybody wants to know, what is the R value? And there are so many things that govern performance, but this is predominantly what people want to know. And the answer is that the energy model will tell you. And so I did a few examples of small, medium, and large wood buildings located in various parts of the Maritimes. And so if you're in Halifax, the same building or a 3,000 square foot passive house would need a roof of R88, walls R54, and slab of R32. And if you jump to Fredericton or St. John's, those R values jump. But if you jump up in size, to a 32,000 square foot passive house, your building in Halifax only needs an R4 roof, which is building code minimum, R30 walls, and an R23 slab. And similarly, slightly higher results in Fredericton and St. John's. If you have a very large passive house, 160,000 square feet, in Halifax, you only need, all of your assemblies are equal to or less than building code minimums, and slightly better performance is required in those two other cities. So you may think, but nobody's, that's a very large wood building, that's a little bit ludicrous. But there actually is a mass timber 18-story building exactly that size, built for the University of British Columbia student housing called Brock Commons Tallwood House. And that building is built with CLT and glulam. And it was erected in 66 days and stores 17 metric tons of CO2e. And I full on thought it was a passive house until I wrote this presentation. So I cheated again, but I had to show you. But here's an example of a passive house certified tall wood mass timber building. It's a 14-story structure made and CLT, and it's a multi-residential building with 62 apartments. It's located in Norway. And the material costs for this building were higher than concrete or steel, but it was offset significantly by the rate of erection. They did about 4 stories per 3 days. And this building was the tallest wood building in the world until the previous building I showed you, Brock Commons, was built. And then BC and Norway kind of traded that title back and forth over the course of a couple of buildings. And this building, I wanted to show it to you because it does, they were permitted to expose the timber. And here's another sort of some design images of that building. It is kind of like a cabinet frame filled with drawers. So each of the apartment units was assembled as an independent module that met the passive house standard and were slotted into place once the framework was built. And I'm going to really quickly go through a handful of other ones. These are all certified passive house buildings of varying building types. So this is the BC Passive House Factory in BC. And the Wood Innovation Research Lab at the University of Northern BC. And Clayton Community Center in Surrey, BC, which is all finished as I understand it, but the opening has been delayed due to COVID-19. It's a beautiful building. And a car dealership there's lots of information on this project out on the internet if you're interested. Um, Particularly challenging given the garage doors. And this one has lost its tag, but this is a supermarket in Germany. And this is a school. And so we are at 3 o'clock, and I'm just wondering, David, what do you want me to do?
Yeah, if you don't have many more slides, I think we could finish up
Okay,
there. But if you got
okay.
quite a bit, we'd end it there.
I'll go through them quickly.
Okay.
These are slides I obviously talked too slow at the beginning, but okay. Um, and so I wanted to go back to form factor because it's happening on one of the projects I'm working on now, where a very articulated building envelope is causing us some headaches. And they're not insurmountable headaches, but it is something that I think was a surprise to the design team. And so if you go back to the 3,000 square or 32,000 square foot passive house in Halifax that I used as an example before, if we build that as a simple box, the surface area is 26. I apologize for randomly switching between metric and imperial. The surface area is 2,625 meters square. But if we take that same building and same floor area and turn it into a more complicated building, I picked a U shape, and increase the surface area by 30%, we need to increase the insulation by 50%. So that has a profound impact on the detailing and on the budget. And if we go to the ludicrous and increase the surface area again, it has an equally detrimental impact on the R values. And so this is not to say that we can't have interesting buildings, but it is something that as building designers we need to be aware of and to rationalize those decisions. And so I am wrapping up with a building that I think did this well. And so this is a small commercial building or a small non-residential building, but it's a house scale. It's only 2,100 square feet. And it's an example of a passive house with a way less than optimal form factor. And the architects, Geologic, who are very experienced and talented architects in Maine, they could have approached this design as a boring box, but they felt that the University of Chicago Department of Ecology deserved a building that responded to the site and the program in a way that was sensitive and beautiful. And so they put a lot of work into making an articulated form. And that's the west elevation. And the form factor is one of the reasons why I'm sharing this building, but the other is because it has a very challenging technical program in terms of building science, in that it is variably occupied, used only seasonally for education purposes, and it has a full-scale lab inside it. So it has a quite complicated and complex energy model work to get it to accurately reflect the loads in the building. So this lab produces high primary, uses a lot of primary energy. And with the super insulation is really risks overheating from the internal heat gains from the lab. So they have tools in there for DNA extraction. They have plant growth chambers. They have a freezer that goes to -80 degrees Celsius, and all of those things, plus human beings and computers and all of the normal things that we have in buildings like hot water heaters. They did a couple of things with the building form. They chose to locate the lab on the north. I don't think that went too far in helping with their cooling loads. And they chose to use a concrete floor slab as a thermal mass to moderate the temperature. and then the ventilation is set up to exhaust heat. Um, and this building is an example of the TJI truss wall that I shared with you earlier. And then you can just barely see it here. This is the south wall. There is a screen that they can close when it gets, when the risk of overheating from the sun or from the south is high. And so they were able to achieve it. And it, because I'm telling you, that is quite an achievement in energy modeling and in architecture. And I'm sharing it because I don't think very many people have ever seen this building. And finally, this is the end, coming soon. This is a building I'm really excited to know more about. It's going to be a certified passive house, cross-laminated timber, net zero carbon building built as a demonstration project by a company called Generate Architecture Studio. And they've partnered with a developer called Place Taylor, and it will use a prefab modular approach. And the really impressive thing, or thing that I want to do next, I guess, about this building is that they're designing it so that it can be disassembled and reused and recycled at its end of life in a very easy way. And so they're thinking of the full circle in this building. And I'm not sure where they are. They're definitely, it's on the design boards and no further. And I'll stop with my list of resources, and you can all jot those down. These are great places to get more information about passive house and wood construction, and also on how to do carbon calculations. And I'm sorry for going over.
No, that's awesome. Thanks, Lorrie. We do have a couple questions here, so we'll just go through them.
Sure, no problem.
Quickly. I think this one might pertain to a particular slide, but what's your opinion on veneer cladding systems supported on multi-story wood projects? It seems counterintuitive to the passive standards to have a continuous steel angle at each floor. Do you have a better detail?
I don't have a better detail. I think you do have to be careful with that, because those thermal bridges have a very profound impact over the loads of the building. So, I mean, I guess what I would say is you need an energy model. Sorry to sound like a kind of broken record, but the thermal bridging will be modeled, needs to be modeled and accounted for in the energy model. And then very likely in those kinds of scenarios, that's going to indicate that you're taking too much of a penalty by using that solution. And so you're either going to need to choose a different cladding or choose some sort of thermally broken approach. Yeah.
Perfect.
That's the quick answer.
And another one here is, please discuss insulation levels on exterior walls versus ceiling systems like aero barrier. If you have limited funds to spend, are you better off with more insulation, an R40 versus like an R28, or spending the money on a ceiling system?
If you have limited funds, I actually think that putting it into air sealing is probably the thing to do if you have access to something like aero barrier. I don't know if everybody knows what aero barrier is, but if you don't, you should go look it up, because you can get to, the performance is a function of the super insulation plus the air tightness. And for some reason, we're always quite fixated on the insulation. And I think that that's because you can put a number on it, whereas the air tightness is, reliant on about 50 million steps that a guy takes on site to ensure continuity of the barrier and a good design. So yes, if you have limited funds, start with aero barrier and then kind of do some math and see how much insulation you need to go from there.
Awesome. And I think this one here is another one that pertains to a slab, but it says, I did not see any structural sheathing on the wall sections. Is the lateral bracing normally taken care of by a shear core, or can plywood shear walls be incorporated?
Well, I wonder which slide that was. It really depends. Like every one of these kinds of projects is going to have a structural engineer. it's funny, I'm working on something right now where we're contemplating, there's sort of some redundancy built into the envelope, and we're like, oh, can we get away without a particular layer of plywood? Because sometimes there's a layer of plywood that you're using, or plywood or OSB, that you're actually, it's serving the purpose as a vapor barrier or an air barrier inside these thick multi-layered assemblies. So yeah, I'm sorry, I'm not sure which slide that was for, so it's hard to know
For
how
sure.
better to answer that.
And the last one, I guess, is really for me. It just says, will you be sharing this webinar? It
Oh,
is recorded and it'll be available on the Woodworks e-learning website. There's all kinds of great other webinars from past events as well on there.
and also, you guys can send me an email.
Definitely. That's good. So I think that's all.
Okay.
Yeah, that's all
Thank
the
you very
questions.
much. And thank everybody for taking the time out of their afternoon.
All right. Thanks, Lori.
Okay. Bye, David.